This is Algebra 2, Unit 5, Lesson 1 on sequences. Now, back in Algebra 1, we did sequences, which are basically ordered lists of numbers. So, sequences are extremely important in mathematics, both theoretical and applied. A sequence is formally defined as a function that has its domain the set of positive integers. Now, remember, the domain would be the term number that you are on. So the first term of the sequence, the second term of the sequence, the third term of the sequence, and on and on and on, however many terms that you happen to have. So your domain must be whole positive integers, because if you're naming something, this is term number 1, term number 2, it can't be negative. You don't have term number 1.5. It's always the term number, so it has to be a positive integer. Okay, so let's look at a sequence. A sequence is defined by the equation a of n equals 2n minus 1. Find the first three terms of this sequence, denoted by a sub 1, a sub 2, a sub 3. Now remember, when you see a sub 1, that means term 1. Okay, so a1 means term 1. a2 means term 2. And so on and so forth. So, to figure out the terms of the sequence, basically you plug in 1, 2, 3, 4, 5 in for n. So, a sub 1, you take the 1, plug it in for n, would be 2 times 1 minus 1, which is 2 times 1 is 2 minus 1 is 1. a2, you plug in 2 for n, 2 times 2 minus 1, 2 times 2 is 4 minus 1 is 3. And a3 is 2 times 3 minus 1, 2 times 3 is 6, minus 1 is 5. Okay, so this is the first three terms of the sequence. So when you see this, the number here is the term number. It's the n in the problem. It's the term number. So n stands for the term number. All right, which term of this sequence has a value of 53? So we want to know when 2n minus 1 will equal 53. All right, solving for n, add the 1, you get 2n is equal to 54, and then divide by 2, n is equal to 27. So the 27th term of the sequence is 53. If you were to list the answers out, 1, 3, 5, 7, 9, and so on and so forth, the 27th term would be 53. Okay, explain why there will not be a term that has a value of 70. Okay, so if I set 2n minus 1 equals 70, I get 2n is equal to 71 because I add the 1 to both sides. And I get, divide by 2, I get n is equal to 35.5. Okay, now what did n stand for in the problem? N is the term number. It is a term number. So there is no 35.5 term. The term number has to be a positive integer. So the domain, which is the term numbers, must be positive integers. Okay. So if you are looking for n, it must be a positive integer. Okay, now let's review recursive definitions. Sequences can also be described by using recursive definition. Recursive, the word recur means happen before. So when a sequence is defined recursively, terms are found by operations on, here's the key word, previous terms. Now, recursive definitions aren't hard. You just have to make sure that you understand the notation. All right, now when you see f of n equals f of n minus 1 plus 5 with f of 1 equals negative 2, you have to be able to interpret this. Okay, so f of 1 equals negative 2. When you do a recursive definition, you have to know where you start. F of 1 will always be the first term of the sequence. When you do recursive, you have to name the first term always, because that's where you start. So f of 1 will equal negative 2. All right, now if I wanted to find f of 2, the second term of the sequence. All right, now if n would be 2 here, what would n minus 1 be? It would be 1. All right, so when you see f of n minus 1, when this is f of n, this stands for the previous term. So whatever term you're on for n, If you're on like the 5th term, this would have to be the 4th term. If this was the 7th term, this would have to be the 6th term. All right, so this means n minus 1 means previous term. Now, this is in function notation. You may also see it in subscript notation, but you'll see it the same way. It'll just be a subscript instead of a parentheses. So f of 2, according to this definition, if f of 2 is the second term of the sequence, according to this definition, I need to know the term before that, n minus 1. So I would need f of 1, and then I'm going to add 5 to it. All right, so what was f of 1? We found that back here. It was negative 2 plus 5, which is 3. Okay, so f of 3. If I have the third term of the sequence, I'm looking for the third term of the sequence, I need the previous term. 3 minus 1 is 2. So that would be the second term of the sequence plus 5. The second term of the sequence was 3, because we did it right here. F of 2 is 3. And plus 5 is 8. So there we go. All right, so the proper function notation when you're doing this, you have to be very, very careful. You have to understand that n minus 1 means the previous term to whatever term that you're on. Okay? So if I wanted to do f of 20, okay, f of 20, I need to know which term. I need to know the 19th term. And then add 5 to it, correct? Okay, so if we think about this for a second, where did I start on this problem? I started at negative 2, so f of 20. To get an f of 20, I got negative 2, and I had to add 5 how many times? I'm going to add 5. How many times am I going to add 5? Well, if I'm starting on the first term and I'm going to the 20th term, I have to add 5, actually, 19 times. So negative 2 plus 5 times 19 should be that term. And that works out to be negative 2 plus 5. I'm going to add it 19 times. And I end up at 93. So f of 20 would equal 93. Now, this is a little bit different. This is what's called an explicit formula. When you're working with this, you have to make sure that you think about how many times did you add. All right, I started the first term, and then I added 5. And then since I started on the first term, to get the 19th term or the 20th term, I had to add 19 more times. So the trick in doing that, you're not starting at 0, you're starting at 1. All right, so let's determine a recursive definition in terms of f of n for the sequence shown below. All right, so be sure to include a starting value. So a recursive sequence, we have to know where we start. So what is f of 1? Well, in this case, f of 1 would be 5, because this would be the first term of the sequence. So this would be the second, the third, fourth, fifth, and sixth. So f of 1 would equal 5. Okay, now, the recursive part of this, we have to figure out what happened between each term. All right, so I'm going from 5 to 10, I'm going from 10 to 20, 20 to 40, 40 to 80, and 80 to 160. What's happening every single time when I do this? I am multiplying by 2. Multiply 2, multiply by 2, multiply by 2. So going up each time I'm multiplying by 2. So what's happening with my recursive sequence? We are taking the term that's previous to it and multiplying by 2. So to describe the previous term, to figure out what f of n is for any term, you have to take the previous term. So using the notation for previous term, if this is n, the previous term would be n minus 1. That's the previous term. And then what's happening every time? We're multiplying by 2. Okay, so that is using function notation, f of n. You may also see it with subscript notation. Usually subscript is more common in Algebra 2, but they kind of go back and forth. So just so you see it, if you did it using the subscripts, usually it's done with an a. You would see it as a of 1 equals 5, because that would be the starting value. And then to a of n, which would be the term of the sequence you're on, the previous term would be n minus 1 times 2. So this is function notation, this is subscript notation, they mean the same thing. Okay, it's just a little bit different. I actually prefer the subscript one because it makes a little more sense to me. Okay, So let's take a look at this recursively defined sequence. T of n equals T of n minus 1 squared plus 2, and T of 1 equals 2. The value of T of 4 is. Okay, so let's interpret what this says to do. Okay, where does the sequence start? Well, it starts at 2. All right, so this starts at 2. And so what do you do with each term of the sequence? Whatever term you're on, you take the previous term, square it, and add 2. Okay, so let's take a look at what we need to know. To figure out T of 4, what term do we need? Well, if we're on the fourth term here, we need to know the third term. So that would be T of 3. We're going to square that and then add 2. All right, so in order to do this, we need to know what the third term of the sequence is. All right, well, let's see if we can figure out the third term of the sequence. We know the first term is 2. What would be the second term? Well, according to this, it says take the previous term. Well, that would be 2. And square it and add 2. 2 squared is 4 plus 2 is 6. All right, so the second term would be 6. Let's repeat that. What's the third term? To know the third term, we need to know the second term squared. Here's the second term. Squared plus 2. 36 plus 2 is 38. So, to figure out the fourth term of the sequence, we've just found the third term was 38 squared plus 2. All right, so 38 squared, let's see. 38 squared is 1444. Plus 2 is 1446. So sequences aren't hard to figure out if you understand what the notation means. So be very careful when you're reading notation of what you have to do. All right, let's look at another sequence. Exercise 5. One of the most well-known sequences is the Fibonacci sequence, which is defined recursively using 2 previous terms. Its definition is given below. All right, so f of n equals f of n minus 1 plus f of n minus 2, and f of 1 equals 1, and f of 2 equals 1. All right, that's a lot of information. All right, so let's see what this says to do. We want to generate values of f of 3, 4, 5, and 6, the next 4 terms of the sequence. So what is the first term of the sequence? Well, it would be 1, because this is f of 1 equals 1. All right, f of 2 is also 1. All right, now f of 3, that is an n value. So if this is 3, what number would this be? This would be 1 previous to whatever term you're on. So if this is 3, this one would be f of 2 plus, well, whatever term you're on here, this would be 2 previous to it. So that would be 2 previous to this one would be f of 1. All right, so let's see, f of 2 was 1, f of 1 was 1, so it's 1 plus 1 is 2. All right, so f of 4, what would be 1 previous to 4? Would be f of 3. And 2 previous to 4 would be f of 2. All right, so f of 3 we just found was 2, f of 2 was 1, 2 plus 1 is 3. All right, what's f of 5? All right, so let's see, this says take the 1 previous would be f of 4, plus 2 previous would be f of 3. All right, f of 4 we found was 3, f of 3 was 2. 3 plus 2 is 5. And then to find f of 6, 1 previous to 6 would be f of 5, and 1 previous to, or 2 previous to 6 would be 4. Let's see, f of 5 we found here was 5, and f of 4 was 3, so 5 plus 3 is 8. So that is an example of a Fibonacci sequence. So being able to interpret what each one of these means is important. Okay, so let's figure out the rest of these in class the next day.